So today I'm going to be talking about rendering. I'm going to try be more informational in this one. First, a bunch of different rendering libraries. The more popular ones are OpenGL, Metal, DirectX, and Vulkan. Don't use that one unless you want to become a Vulkan programmer. But the most annoying part is that all of them don't work on every platform. For example, Vulkan works on Windows, Linux, and Android fine. macOS and iOS requires Molten VK, and it doesn't work at all on web. So what to choose? None of them actually. There's many libraries that are abstraction layers. Basically, you are a single code base for your render, and the abstractor will choose the best backend for their operating system. There's many different ones, like so-called SFX, SDL, and the one that I use, WGPU. These abstraction libraries make GPU programming a lot more enjoyable. Now pipelines. This is the main part of the render. There's three main stages: vertex shading, rasterization, and fragment shading. Then often enough there's more steps added on by new games, but not always. Some of the more notable ones are geometry and mesh shading, backface culling, and alpha blending. Let's first focus on vertex shading. It goes through every mesh and object and turns it into camera space. There's generally three main spaces: model space, world space, and camera space. Starting off, it's in model space. Every vertex has an X, Y, and Z component. If you're in 2D, the Z is replaced with a Z index. The vertex is turned into world space from the position, rotation, and scale of the mesh. Lastly, the vertex is changed into camera space by utilizing many matrices such as translation, scale, and rotation. This will give a final X, Y, and Z value of the vertex. Once three vertices are changed into camera space, they can be connected into a triangle. This gives us a final shape in the end. Next, rasterization. Rasterization turns the triangles into pixels on the screen. It then generates fragments. A fragment is a single pixel from the triangle with textured data, such as depth, color, normals, etc. You may notice that some triangles shouldn't be seen by the camera. This is fixed with a Z buffer or a depth buffer. When we are turning models into camera space, we get this returned Z value. This is important now. A lower Z value means it's closer to the camera than triangles with a higher Z value. But since the vertices of the triangles are in 3D space, this means the vertices will all have different Z values. So each pixel will have a depth value. This depth value is appended with the fragment. Now fragment shading. In short, fragment shading just tells what color the fragment should be, and there's some fragment shaders that utilize lighting effects. Flat shading gets the normal, the way the fragment is facing, and compares it with the light source. If the fragment is perpendicular to the light, it's darker. If the fragment is facing the light, it's lighter. But if we run this on a ball, you can see that it's not smooth. To fix this, instead of having the triangle flash, it can be slightly rounded to make it appear more round. Now there are more advanced techniques. First, super sampling anti-aliasing, or SSAA. After rasterization, you may see that the triangle looks jagged and rough. When a mesh is being rasterized, it adds 16 sampling points in each pixel to smooth it out. A sampling point is similar to a new pixel, but this pixel isn't being drawn. Depending on how many sampling points are filled in, a new fragment is added to that triangle, but with a slight transparency. Next, NVIDIA's DLSS. Quick note while I was editing, AMD has a similar thing, but it's actually called FSR and may also work a different way. There's two main types of DLSS, super resolution and frame generation. Starting with super resolution upscales the final image into a higher resolution. Super resolution uses a neural network. For frame generation creates a second frame in between two frames. It does this by getting the most recent two real frames and uses another neural network to generate another frame. Recent GPUs can generate up to 3 extra frames. Lastly, ray tracing. Ray tracing is actually its own pipeline. Newer games may use a mixed pipeline, where it uses a ray tracing pipeline along with the pipeline we talked about before and merges them. It sends out a raycast for each pixel on the screen. Once it hits a triangle, it bounces off and blends the colors with the other triangles it bounces off until it bounces off too many triangles or goes too far from the camera. This can create some photorealistic scenes, but it's very GPU intense. It's the end of the video. This actually was a lot of fun to make, but took a while. In the back you can see the scenes that I used to make this video. Even though this wasn't really a devlog, it's still to do with Vyxen. Anyways, bye!